Now let's consider the slightly more difficult situation where we have two shark objects within our image. Now you and I looking at this image can clearly see that there are two distinct regions. We're not confused at all. But for the machine vision system that we're building, we need to develop an algorithm that can determine that there are two distinct regions here. If we apply the technique of moments that we just looked at and compute the moments of this scene, what we will end up with is the centroid of a region which contains the two sharks. We see the centroid in between the two sharks. It hasn't been able to work out that they're separate. It's just treated all the white pixels in the same way. We see also the bounding box is drawn around the extremities of both sharks rather than around the sharks individually. We need some way to distinguish between these two objects. Now the way that we do this is to transform the image. So here's our input image, and we're going to perform a transformation. It's a process called connectivity analysis, and the output image is shown on the right. We refer to this as a label image. And what's interesting about the label image is that all of the pixels that belong to the same object are assigned the same label. So we see that all of the pixels that belong to the top shark have been labeled 1. All of the pixels that correspond to the bottom shark have been labeled 2, and all of the pixels that belong to the background have been labeled 3. In this image, the pixel values refer to the label of the object, if you like to describe which of the n objects within the scene those pixels belong to. This is a really powerful transformation. The white objects in the input scene are called blobs. Blob is actually a technical term, you're allowed to use it. And in this input scene there are 3 blobs, shark 1, shark 2 and the background. And in the output image the pixels have got values 1 to 3 indicating which blob they belong to. So what is a blob? Well, it's also known as a region, and sometimes it's called a connected component. It's a set of contiguous pixels of the same color that are next to each other. They touch each other. And when we talk about color, before we've just been looking at a binary image where the pixels are either black or white. Oftentimes we'll start with a real color image, and the first processing step is to convert that color image into a binary image. So in the top example here, we have a scene with 4 yellow objects in it, and we perform some image processing operations, and we'll talk about this in future lectures, to convert the yellow pixels to being true or white and all the other color pixels to being false or black. In the bottom example, we're trying to find the tomatoes on the bush, and we're going to use image processing techniques that give us a true result when the pixel is red and a false result when it is not red. So the first step is to take a real color image, convert it into a binary image where the pixel values are either true or false, and then we can apply our connectivity analysis to that image. The label that we assign to a pixel indicates which set it belongs to. Every pixel has the same label as its neighbor to the north, south, east or west that has the same color. This is a fundamental part of the connectivity analysis algorithm. Now this process of performing connectivity analysis has many names. Sometimes it's called connected component analysis, sometimes it's called blob or region or image labeling, sometimes it's called blob or region coloring. Many names, the same algorithm. Here is our original binary image with 2 sharks in it, and now in the middle we have the label image where the pixels have got values of 1, 2 or 3 depending on whether pixels belong to shark 1, shark 2 or the background. Now I can apply a simple logical test to this image, and I can say give me all of the pixels that have got a label value of 1, and I end up with this binary image that contains just 1 shark, the top shark. And once I have this image, I can apply the techniques we used previously to find the centroid and the bounding box of this particular shark. Now I can ask for a binary image which contains all of the pixels that are labeled 2, and I have an image, a binary image, which contains just the bottom shark. Once I have this shark in isolation, I can apply the earlier techniques and again find its bounding box and its centroid. Now the background is also a blob. It's all of the pixels that are labeled 3. So we can say what is the image where all the pixels are equal to 3, and we see it here. It is basically the background with shark-shaped holes in it. It's a blob as well. It's a very large blob. It touches the edge of the image and it has got these 2 holes in it, which are the objects in the foreground. If we compute the moments of the background blob, we find that it's got a centroid which is roughly in the middle, and it's got a very large bounding box which goes around the whole outside of the image. Now we have a binary image, or logical image, that contains two blobs. So let's compute the label image. The function that we use has actually got two output arguments. So the first output argument, L, is the label image itself, and the second output argument is the number of blobs that it finds within the scene. The function itself is called iLabel, and we pass in the binary image. So it's computed L, which is an image, and the number of blobs, which has got a value of 3. So it's saying that there are 3 blobs within this scene. There are the 2 sharks and the background blob. So let's display the label image and investigate that. We'll start a new figure and display the label image. Let's have a look at some of the pixel values within that. So these pixels here, all the ones that I'm clicking on, have got a value of 3. That means these pixels belong to blob number 3, which is the background blob. All of these pixels here in this shark, all labeled 1. That is, they all belong to blob number 1. These pixels down here all have a value of 2. So these pixels all belong to blob number 2. Now what we can do is use a logical operation, a logical test on the label image in order to isolate the different blobs within the image. So what I can do now is to display all the pixels who have a label equal to 1. And what we see now is there is just a single shark in the scene. Let's have a look at all the pixels that have got a label value of equal to 2. And now we see the second shark. So now what we've got is a scene with a single blob in it. And this is a problem that we've met before. We know how to work out the bounding box of a scene that contains a single blob. We know how to compute the centroid and the area of a scene that contains just a single blob. So by using this intermediate step of labeling the image, we can turn our complex problem with multiple regions into a problem that we have seen before. Now, an extra level of sophistication that we can go to is to use the function iBlobs. And what it will do is I pass in the image. That's all I need to do. And it's returned a vector of blob objects. Actually, technically, they are region feature objects. And there's one object for each region or each blob in the scene. So element number 1 is a blob with an area of 7,827. We can see its centroid. We can see its color, that is, it comprises pixels with a value of 1. We can see its label. It's got a label value of 1. And a couple of other parameters as well that we will get to in due course. Blob number 2 also has an area of 7,827. It's another shark. And blob number 3 has got a very large area, and we can see that its color is equal to 0. So that is the background blob. Let's show again the original image. Here we go. There's the scene with the 2 sharks in it. For the first element in this vector of blobs, that's blob number 1, I can plot a bounding box. And I can do that in the color green. And there we go. For blob number 2, I can plot its bounding box in green. I can also plot the centroid of the object, and I will plot that in blue, and I'll draw an asterisk there. The blobs have also got a number of parameters or attributes. So for instance, for blob number 1, I can say what is its area. We can look at the color of that particular blob. We use the class attribute. We see that it is comprising pixels with a value of 1. We can look at the centroid using the P attribute, and we see a vector here which contains the U and V coordinates of its centroid. We can get the individual elements. UC is the U coordinate of the centroid. We even find the moments have been stashed away, so the 0, 1 moment of that particular blob has got this particular value.